Okay, so here's Unit 2. This is on forces and fields. So we're going to talk more then about the four main types of forces that exist in the world. I think this was on one of my first slides, actually. Physicists have realized that there's four natural fundamental forces. Now, I'm not talking about like when I apply a force and I throw something. Sorry, that was a bad ricochet. Are you awake, Jessica? Yeah. Okay, sorry. Didn't expect that. We're talking about natural forces that we seem to find around the Earth. And one of them we've talked about already. Can you guys think of which natural force we've already talked about? Gravity, good, yeah. So the next main force is the topic of this unit. It's the electromagnetic force. So there's actually two forces kind of, originally people thought that they were separate. They thought that electrostatic, like static electricity, and you ever rub a balloon on your hair and then stick it to the wall? That's a force, basically, right? Static force. There's also the force of magnets, but they're actually related. There's actually a huge link that actually causes one to go to the other. And it's actually the basic premise behind how we do things like motors and generators. Your car motor, or like the generator that you have as a backup generator in case power fails, they both operate on similar electromagnetic properties. So we'll talk about those going forward. By the way, the other two types of forces, we will get to one of them later in the course. There's the strong and weak nuclear forces. Strong and weak nuclear forces. The weak nuclear force would be things like radiation, like alpha, beta, and gamma radiation that happens when you have nuclear decay. And we'll get to that in our last unit. The other one is one that I don't even know that I can describe all that well. That last force is not in this course, by the way. It's basically the force that keeps the nucleus together. You know how a nucleus is a bunch of neutrons and protons? As we're going to talk about even in this section here, protons are positively charged. What should positively charged things do to other positively charged things? It should repel them. By all logic, the nucleus of all atoms should basically tear itself apart and rip itself away. Furthermore, what should electrons do when compared to a nucleus? Well, electrons are negative, protons are positive, right? Should electrons not want to spiral into the nucleus and basically have all of your protons should want to rip themselves apart, and yet around that nucleus where you have those electrons everywhere, shouldn't those electrons not want to stay out here? Shouldn't they want to get sucked into the middle? And yet they don't. And so physicists have a hard time trying to describe what the heck is happening there. All we can see is the effects of what's happening. We know what happens. We don't necessarily know why it's happening, but we know what happens. Does that make sense? And so they deemed that the strong nuclear force, I believe. So anyways, we're going to start talking more about the second force I mentioned there, the electrostatic, the electromagnetic stuff. And this is pretty cool stuff. It's got huge applications. So I'm going to start our lesson today, hopefully this works, with a YouTube video. And what I've got on the next couple of slides, if you guys can fast forward here, is I've got 1, 2, 3, 4 different sections here where the person in this video is going to describe some contributions in history, people who have been involved in the field of electrostatics. We're just going to talk about the electro part right now. We'll get to magnetics later. So as I watch the video, can you guys throw in a couple of notes on the following slides, just about what the video talks about? And for Brady and Tom, you guys are going to want to crank the volume as best you can. And if this doesn't work, I might have to show you the YouTube video later. So we'll see how this goes, whether you can hear this over our speakers.
Welcome to the history of electrostatics. If you ask people who discovered electricity, they will tell you names like Benjamin Franklin, that's the dude that flew his kite in a lightning storm, or Thomas Edison, the man that created the light bulb, or Alessandro Volta, the creator of the first battery. But these people had nothing to do with the discovery of electricity. Electricity was first mentioned in the works of a Greek scientist named Thales of Miletus in about 600 BC. Thales noticed that if amber, which is just hardened tree sap, was rubbed, it had the ability to pick up dust and leaves. What he was seeing is what we now call static electricity. Another Greek named Theophrastus noticed in 300 BC that other substances had static electricity if they were rubbed. Unfortunately, Neither Thales nor Theophrastus had any scientific explanation for it. They just thought it was interesting. What they did realize was that sometimes the two objects that are charged would attract each other, and sometimes two charged objects would repel each other. This developed an idea that there were two kinds of charge. Today, we call the one positive, and the other one we call negative. We say that like charges repel, and unlike charges attract. In 1600 AD, an Englishman named William Gilbert started studying these phenomena. He wanted to come up with a good scientific explanation for these ancient discoveries. He was actually the first person to use the word electric, which is a variation of the Greek name for amber. Although he had only some success in describing electricity, he was able to show that there were differences between magnetism and electricity that seemed to indicate that they were completely different things. For example, an amber rod has to be rubbed to have electric effects, but a magnet is always a magnet. It doesn't need to be rubbed. Up until this point, scientists all believed that electricity and magnetism were just different versions of the same thing. Then came Benjamin Franklin, 1706 to 1790, and he started his investigations after Gilbert. Yes, he did fly a kite on an overcast day. No actual lightning, but he wasn't the first person to do it. Several people had tried to do it before him to prove that lightning was electrical, but they'd all been killed. Most people thought that he was a nut to do it, but in fact he had his son set up most of his equipment while he stood back. Franklin was able to prove that lightning was a discharge of static electricity, but this doesn't mean he discovered electricity. Most of Franklin's research actually focused on amber rods and glass rods. It had been found that if a rubbed amber rod was dangling from a string and another rubbed amber rod was brought near, the dangling one would move away. If a dangling rubbed glass rod was brought near to a rubbed glass rod, the dangling one would move away. If a amber rod, which was rubbed, was brought close to a dangling glass rod which was rubbed, the glass rod is attracted towards the amber rod. Therefore, the charge in the glass must be different from the charge in the amber. Franklin decided to say that the glass rod had a positive charge, and that the amber rod had a negative charge. We use ebonite today in place of amber. Why did he choose glass as positive and amber as negative? Well, no real reason. They were just different and opposite to each other, and so he picked one to be positive and the other one to be negative. He then came up with the fluid theory that said that all substances in the universe contained this electric fluid. And this electric fluid was positive, and a positively charged object had more of this fluid, and a negatively charged object had less of this fluid.
Pause that for a second here. One of the things that we discover in science a lot is that when people start doing science experiments and they have no real clue what they're doing, all they can do is just see random effects here, then they have to start naming stuff, right? And Benjamin Franklin decided to randomly name stuff positive and negative, and the guy just said in the video there, he had no real reason to name one or the other, he just named one, right? And he had this theory that there was this fluid that was more positive. Some stuff had more positives in it than negative than others did, right? And we now know that that's actually quite incorrect, because what is electricity the flow of? Yeah, it's not positives that move around, it's actually the negatives that move around. And we'll see how this comes to play later, is that there's something called current, there's something called conventional current. And regular current is just the idea that electrons move from one side to the other. But if you ever hear the phrase conventional current, it's based on this historical idea that they didn't realize this because they didn't even know electrons existed back then. It wasn't until like the Rutherford experiment much later that they knew something about this. But if you ever hear conventional current, that's basically the idea that positives move, which we now know is incorrect. Does that make sense? So I just wanted to point that out right here, that Franklin just had to name it something. So he went positive, negative, and he may actually have it kind of backwards.
Now, although Franklin's single fluid theory is not exactly right, it did lead into a law which we still use today in physics:
And this is on your sheet, I believe, like one of the 10 laws.
conservation of charge. Charge cannot be created or destroyed, but it can be separated in an object or be transferred from one object to another. Sometimes, in the past 100 years, it has become clear that these charges depend on the makeup of the atom itself, not on some fluid. The nucleus is made up of protons, which are positive, and neutrons, which are neutral. And they're surrounded by a sea of electrons, which are negative, in orbit. In a normal state, the electrons and protons, they balance out, and so the charge in the atom is neutral. In our example here, we've got 6 positive protons and 6 neutrons, which are neutral, inside the nucleus.
Just going to pause it there. There's a lot of overlap between chemistry and physics, which I like because I'm a chemistry teacher. And let's see, I taught all you guys come last year. And you guys, we did a pretty healthy amount of chem in grade 10. So does anybody look at this photo here and you recognize this as something you've seen before, the idea of the nucleus with electrons around it? Okay. To use the proper words, not even just in chemistry, but now in physics as well, this would be considered an atom. Atom because the amount of electrons equals the amount of protons. You guys remember that vocabulary? Atoms are one for one, basically. 6 electrons, 6 neutrons, 6 protons. You guys remember what happens, what we call it, when it's not the same? It's known as an ion. Yeah, and there's 2 different names. There's the cations and the anions. You guys can write that one down if you want, because we'll use this vocabulary. Cations are positive, and anions are negative. So I think we show it in the video here, but just to make sure we're clear in advance, how do you make a cation? How do you make something positive? Yeah, you cause something to lose an electron. Now, on the previous slide, though, they mentioned there's this law of conservation of charge. You're not really losing an electron. The electron is just going somewhere else, right? In an ion, maybe somebody else is stealing the electron. When we talk about this electrostatics unit, sometimes you can have the buildup of electrons on things. I've been messing around with that Van de Graaff generator in the back there. The Van de Graaff generator is something that basically tries to accumulate a lot of electrons. It rubs the stray electrons off of some other stuff and steals the electrons away. Does that make sense? Which then makes it turn into anions, because anions have extra electrons. They've stolen the electrons. You guys remember that terminology? Let me keep the video going.
Then we've got 6 negative electrons in orbit around. Therefore, the carbon atom is neutral. Sometimes the atom may lose or gain electrons. Nothing happens to the stable nucleus made up of protons and neutrons. It is the electrons that are being stripped off or added on because they are on the far outside edge of the atom. If the atom loses electrons, it will have a positive charge. If it gains electrons, it will have a negative charge. Either way, it's now called an ion. Let's have a look at this example. The sodium atom has 11 protons and 11 electrons. Sodium has a tendency to lose 1 electron. That means it's got 11 protons and 10 electrons. The net charge is a positive 1, making the sodium cation. Chlorine has 17 protons and 17 electrons. It tends to gain electrons. Chlorine gains 1 electron, will have 18 electrons and 17 protons. The net charge is a minus 1, and that's the chloride and ion.
Let's just talk about some of the brief highlights that you might have written down here then. So, Tales of Miletus. I mean, we're talking like ancient Greek philosopher time, right? Like this is back in the age of like Archimedes and Aristotle, you know, some of those sorts of names, right? I mean, basically his vision, what he discovers is that stuff is sticking randomly to this amber. Do you guys know what amber is? Ever seen it before? My daughter has an amber necklace. When they sometimes people think they help when kids are teething. Like when Cammie was punching out her teeth, they use like amber in the necklaces. It's basically like hardened tree sap. Right? Now I don't actually know whether it really helps with kids when they're teething or not. Some people think it's just totally bogus. But what Tales discovered was that stuff was just randomly sticking to it, and there appeared to be a force of attraction that was causing like lint and dust to attract to it, getting stuck there. Right? What he didn't know at the time is that it was an accumulation of electrons, and that negative charge was causing positively charged dust to basically stick to it. Does that make sense? But I mean, they had no idea of positives and negatives yet. All he was able to do was see, like the wind, the effects of what was happening. Does that make sense? But explaining why it was occurring and knowing all the intricacies behind it was so much more difficult, right? Because they didn't have the ability to know what was happening on a molecular level. We're actually not even talking molecular level. We're talking like a submolecular level, where like there's nothing to see. There isn't like a transfer of like from here to here where there's like something in between it. That's one of the cool things we're getting to here is Einstein once called this action at a distance, I think, where he coined that term, where the idea is, normally if that chair is going to move, it's because I push it, right? But now we're talking about forces that occur from here to there, where there is literally nothing in between, and yet it's still moving. Why? All right, that's Tails on my list. I forget what they wrote down about Gibbard again. What did you guys make out of? What did he do? Was he the guy with the crystal with the rods, or was that different? Say that again? Oh, he thought there were similarities, right? Okay, so there were these two similar but different things where people had found magnets, and they realized that magnets were doing what I just described. You had two objects right here, and yet they would stick together for no apparent reason, right? And it had a lot of similar properties to electrostatic stuff. And so this was the beginning of them starting to realize that these two things are actually quite intertwined. They didn't realize it yet. I think he was the one who kind of concluded that there's similarities in that, yes, stuff will stick together, but differences in that, in order to make this work, they had to use like a rod, and they had to like rub it with either silk or fur or something like that. I was actually messing around with those the other day in the classroom. You guys will even do this in our lab, hopefully. In order to make the charges, they actually had to do like the whole rub the balloon against your hair, and then it would stick against the wall. They had to actually do something. Whereas magnets were always magnets. You didn't have to like rub a magnet against your head to make it work. You know what I'm saying? Franklin, probably the biggest highlight I want you to get out of Franklin is that he's not as awesome as the books make him out to be. Did you catch the subtle little thing there about him not doing his own experiment? Let his kid do it. And yet he gets credit for it. He's like, hey, you stand up there with the kite in the lightning storm. By the way, everyone who's ever done this before has been electrocuted, but you go do it, kid. And I'll take credit for it for the next 200 years. Boy. Anyways, his theory basically of positives and negatives was excellent. It's something that we used going forward, the idea of positive and negative charges, except I think he kind of had it backwards. He thought there was this fluid made out of positives, but it's really not positives that move, it's negatives that move. And I wouldn't really call it a fluid, so to speak. But negatives do move, right? That's basically the function of electricity. As negative charges move through a wire, that's electrical current. So kind of right, but kind of backwards. Science is full of things like this, where someone makes a discovery, and they name it something, and then later we discover, why did we name it that? That was a dumb name, because it's kind of wrong. But like they were close, if that makes sense. Okay, and then the last slide here for modern theories. Now we know more about it. We're going to talk about these in our last unit, but you should maybe recognize the phrase the Rutherford experiment. You guys ever heard that one before, the Rutherford experiment? Anybody know what it was? It's known as the gold foil experiment. What did he do? I think he shot alpha particles, but he shot something very small through, and he was trying to shoot it at a sheet of gold foil. And normally you'd think that gold is solid, and what would happen is the particles would bounce off the gold foil and just bounce right back at you. But that's not what happened. What ended up happening is a lot of the particles that he shot at the gold foil went right through the foil. And it allowed him to think that maybe all of the mass is actually in the nucleus. He thought maybe there was a nucleus in play. And that rather than there being positives and negatives just randomly interspersed, he figured that the negatives were here and the electrons were randomly orbiting. And that's what allowed the particles to kind of phase through the gold foil. You guys heard this one before? Okay. I don't need you to know it now because we do cover it later, but really his experiment is what allowed us to come up with the concept of electrons being free to move because of a nucleus packed with protons. So just write down the Rutherford gold foil experiment, And we'll look into it in the unit where it actually is tested on. So that was a big part of us realizing now this current model of the atom with nucleuses and electrons. So, okay, so let's move forward from there. Now that we've covered like 4,000 years or 2,000 years of history, now we can finally talk about what we believe to be true, these ideas of electrons. Okay. Electrons that are capable of moving. And you guys probably already know this. Some things are just better at conducting than others. And so there's kind of like a continuum here of things that don't conduct through to things that do conduct. Maybe a metal that conducts electricity. What do we make our wires out of? Yeah, copper is a good example, right? Copper is much more on the conductor side here, where it's going to allow electron flow. Right? Now, if I want to prevent myself from getting electrocuted, maybe what I'll use, like for example, on the outlet of the toaster, you know, you don't literally plug the metal directly into the outlet because you might get a shock there, right? So we wrap the metal in something that's considered an insulator, like say a plastic polymer or rubber. Rubber is a good insulator. Paper is actually a really good insulator. Right? Now, I want to make sure we use the phrase properly. There's insulators for heat, and then there's insulators for electricity. Similar but different properties there, right? Where some things allow heat to transfer very well. We're specifically talking about the transfer of electrons. Right? So if you were to stand outside with a metal pole in a lightning storm and hold it up, there's a good chance that you're going to attract, that metal pole is going to attract the electrons, you know what I mean? And you get electrocuted. Whereas cars are actually fairly safe to drive through because of the rubber tires on them, because it actually grounds the electricity. There's actually something called superconductors, and I'm not overly familiar with how those work. I believe in order to make superconductors, they sometimes have to play with temperature and stuff like that, but there's kind of a continuum here where these guys do not allow charges to move, and these guys do allow charges to move, and these guys do a really good job of it. So, here's a table I found on the internet that, you know, basically kind of illustrates the concept here. If you're looking for good conductivity, copper is the main one that we make things out of, and aluminum's pretty good, whereas like rubber, wood, you know, those guys right there are not good. The cool things are actually the ones in the middle. People have started to recently figure out how to use things called semiconductors, where they have the ability to conduct, or they don't have the ability to conduct. And you use them in things like the computer chips and transistors, where you want to sometimes have current flowing, but then later you don't want the current to flow. You want to be able to turn it on and off, essentially. Does that make sense? So there's actually kind of a cool use for those in anything electronic now we use semiconductors. You may have heard of things like before where you want to put like a surge protector on like your computer or your electronic devices because you might fry the circuitry. If you were to have too much voltage or current, I don't remember which one it is, run through your devices, you can actually blow those sorts of transistors or computer chips by having too much voltage or current spike through them. You ever heard that before? You want to be careful of that? Here's a slide, just you guys can read through it here. Most metals are conductors, most non-metals are insulators. Semiconductors are capable, but it depends on the conditions. Apparently photocopiers have semiconductors in them based on selenium. And I guess the concept is that it's based on exposure to light. And that's actually the whole principle behind how the photocopier works. Is that if the light is on, and you know how like they run the light through the bottom of the photocopier there, how that light goes through there, then apparently that's like the basic principle. I don't know the whole details here, but as the light runs through it, that's what allows you to either, yes, reprint a dark image, or no, don't reprint a dark image based on how the light reacts with like the particles going on there. So, I don't know, research it if you care. Okay, superconductors, apparently, like I said here, they need to be like close to absolute zero. Now, I don't know a ton about this, other than in chemistry, you guys remember talking about absolute zero before, right? It's in theory the lowest possible temperature possible. And the reason why this would be different here is that there would be no movement almost, right? Like there's no residual energy transferring. Like, you know how all particles would vibrate normally? Well, if you freeze this thing down to basically 0 Kelvin, apparently then there's no vibration of molecules anymore. And apparently that makes it really, really easy for the electrons to flow through stuff. So then the electrons just zip through this superconducting material. So this is where, as a physics teacher, like you guys don't know this going in here, I can tell you and regurgitate information, but if I knew more about this, I would be working in these fields, right? Like people who actually do this stuff would be like Sheldon and Leonard off of Big Bang Theory when they're working with like super cool helium or whatever they're doing if you watch those shows. It's like, this is super cool fields, but I only know this much. People who really know what they're talking about, like they're the ones who go do these jobs. So, all right, moving on. Here's what we have kind of discovered then. The idea then that if you bring something charged, the electrons are capable of moving. This is often called a pith ball. You ever see that in a note or in a test question or something like that? We call it a pith ball, where basically it's just a neutral ball that would just hang from a string. And although it doesn't really have the positives and negatives spread out like this, because we know that's not how atoms actually work, what we're trying to represent here is that this thing is neutral. There is even charge on it. There's no extra electrons. There's no fewer electrons. Does that make sense? Now, what we could do actually, this is known as induction. I'll just underline the word here, induction. If you were to bring a negatively charged item near it, well, you know how electrons are able to move? What ends up happening is all of the electrons would then try to push themselves to the far side of the molecule, or to the far side of the pith ball, because what do negatives do to other negatives? They repel. Does that make sense? Now, what it does is it induces a dipole. We've used that word in chemistry before, a dipole, the idea that on one side it's positive, on one side it's negative. Now, this is not an accurate picture here, because really, are all of the electrons on this side and all of the positives on this side? Well, no. If I were to draw a better picture, it might look like there's positives, nucleus is here, there's negative electrons around all of them, and some of these negative electrons then would just work their way to the other side. Right? There still would be some electrons over here. Not every single electron is going to move. Not all of them have that ability to, right? But hopefully you can kind of see this idea here. What it creates is a temporary dipole where this is positive and that's negative. That makes sense? So that's known as induction. Do I have that word highlighted here? I don't. We'll talk about it later, I'm sure. Induction. There's different ways to charge items. We'll do this in our lab when we get around to it, whatever the day was here. But one of the ways you can do it is by like rubbing like a fur against what's called ebonite. Did you guys hear the guy in the video point out that we used to use amber? Used to be amber. But now they use ebonite. This is black hard rubber stuff. Here, I'll even grab it because I got it back here. I'll show you how this looks. You guys can see that? Oh, you're not going to be able to see that very well. Okay. So here, you guys can see these. This would be like a hardened black rubber plastic. So this would be like ebonite. And what we've discovered is that if you were to take a fur, so I've just got some sort of pelt here, if I were to rub this along here, kind of similar to the whole balloon on your head sticking to the wall sort of thing, what I can do is I can make this thing become become the rod become negatively charged. Why is this becoming negatively charged? Well, what we're doing is we're taking stray electrons off of the fur and we're adding them to this guy right here. And so now this would have a negative charge on it. Now, I want to show you guys, this is called an electroscope. And sorry to Tom and Brady, you guys won't be able to see this very well. I'm not going to touch this. Can you guys see these two little leaves right there? You guys see there's two of them right there? Oh, come on. I know, this is frustrating. This is why I wasn't planning on doing this, because I was going to leave it for your lab. You guys see that? I didn't touch it. There's grounding in here, right? So what's happening here? Let's talk this through. I've now ideally made this thing negatively charged. This is negatively charged. Now all of this stuff over here is neutral. Now if I bring this negatively charged object near there, where are all the electrons going to want to go? Are they going to want to be near the ball at the top? Well, no. The electrons are going to want to get away from all the other electrons. There's so many electrons on the end of this stick right here that these electrons inside here want to get away. So where do they go? Well, they go as far away as they possibly can, down to the bottom of the tips of those two leaves right there. You just had an aha moment to explain it. What happened? Say it again?
The two ends will help
Yeah. So see how there's two leaves in there, right? Well, if all of the electrons, let's say each of them go halfway down each of those two leaves there, right? Now these two leaves down here are both negative. What do negative things want to do to each other? They want to spread out. This is the exact same principle of the Van de Graaff generator when we try it out. When someone uses the Van de Graaff generator and they've got, like, say, the girl with the hair that just frizzes out everywhere, what's happening is there's so many electrons and so much negative charge getting accumulated on the person that their hair basically tries to move away from itself, right? That's why it goes in as many directions as possible, because this one's negative, that one's negative, this one's negative, and they spread out, just like this one here is ideally going to spread out. Does that make sense? So this is known as an electroscope. I'm going to have you guys try to do some lab work with them and play around with them. I have the stuff for this, but I think I've made my point. You can actually do the same thing with silk and glass. And what you can do is you can rip the electrons off of the silk, off of the glass onto the silk, and it actually makes your glass rod then positively charged. Right? Here, what we're doing is we're taking extra electrons from the pelt and we're adding electrons to the stick. So this has more electrons. In that example up there, what should be happening is you're ripping the electrons off of the rod, and so the rod has no electrons left. It now becomes positively charged. I have a word down here that I pulled from chemistry. It's the word electronegativity. It basically is the affinity for electrons. Certain things just seem to want electrons more, and other things don't want to have electrons. And so I found a couple of tables here that we can use as we need to figure out kind of who wants electrons. Sulfur and brass and copper, these guys want electrons. So our ebonite rods are not too bad. Basically, we can give them more electrons because they want to hold on to them. Whereas our glass does not want electrons very much. It very much wants to get rid of them. So if you were to then rub the ebonite rod with fur, we just were to use those two right there, ebonite against fur, well, what's going to happen? Well, the fur is going to want to give its electrons to the ebonite. Does that make sense? Which is why this guy right here becomes negatively charged. Whereas with, like, say, glass and silk, glass is going to want to give its electrons away to silk, meaning that the glass becomes positively charged. So if you kind of know which items work with which, it gives you the ability to make items that are charged, so you can do that cool little thing right here. So here's a better table. Whatever. Okay, so I just finished talking to you guys about something called induction. Okay, so one more time as a demo. I am not going to actually touch. This is that whole, as I think was Einstein. I hope I'm cribbing it to the right guy. He called it action at a distance. I'm going to cause something over there to occur, and I am not going to touch it, right? I am putting the stick right here. I haven't actually touched it yet, and yet down the road somewhere, something occurred, that action at a distance. Okay? This is known as induction. I am inducing a charge in these things where the negatives cause the electrons to run down there. That's induction. Okay? Conduction is similar, only I'm actually going to touch it now. Okay? So watch what happens again here. When I put this close by here, the leaves separate, right? But as I pull it away, the leaves go back. Shouldn't they? Shouldn't all the electrons that got pushed down to the bottom of those two leaves there, shouldn't they basically be able to go back to their natural positions? Well, what happens if I do this? I touched it. Now it stays apart. Why? I've actually transferred the electrons. The electrons aren't now just stuck on the stick, but the electrons actually went through the electroscope, and now there's lots of electrons inside there, right? So much so that there's now extra electrons there, and they're stuck, right? In a way, this is now negatively charged all inside there. There's extra electrons in there, and therefore the ones down at the bottom are going to want to repel each other, right? Now, if I want to get rid of those electrons, the phrase we would use is we say that we would ground it, right? So if I were to do this, what just happened? Where'd the electrons go? I have them now, right? And they've now gone through me, and they're, they're spread out. They're in the chair. They're in my clothes. Does that make sense? All right, and this is the same sort of principle, like how say you use like your socks on carpet, and you kind of rub your feet on the carpet, and you go zap your friend. Anyone ever done that before? Right? In a way, what you're doing is you are picking up a lot of extra electrons. They're working their way through your body, and then you're kind of discharging the electrons into your friend. Right? That's kind of what I've done right here. There's a whole bunch of extra electrons right here, and I'm just zapping them back in through me. It's not enough that there's an issue with it, though. Okay. Wait, here's what you guys need to know. I need you to know the word conduction versus the word induction. Okay, that terminology is going to get used a lot. So make sure you know which one is which. Conduction, you're actually touching things, and electrons are moving through one item to the next one through physical touch. Right? Induction is action at a distance. Something is going to move, but we're not actually having things touch each other yet. Okay. Now the charge will transfer, and what should ideally happen is the charge should even out. Okay. Now, again, a lot of these diagrams, they're not accurate in the way that this is how molecules work or atoms work, but we can use it to illustrate it. Imagine this is an object that is positively charged. Okay, now again, in order to become positively charged, it actually means that you have to lose electrons, right? But ignore that fact right here. Let's say this has excess positives. Well, if these two items touch, would it not make sense that the positives would then spread out amongst both of them? Now, did the positives actually move though? No. So this is where the diagram fails. It's not like this positive moved from here to here. What actually occurred is some negatives went that way. The electrons are what actually moved. Right? So this guy would have had a positive for every negative. Right? Every positive would have had a negative. And then a couple of, when they touched, the negatives would have come over here, and this negative and that positive would kind of balance. And this negative and that positive would kind of balance. It looks, the effects of what we see look like the positives have moved from here to here, but that's not really what happened. But we can still use this diagram to kind of illustrate the concept. What I need you guys to know is that whatever charge you originally had, well, if you have two objects, it'll be cut in half. That's all. If you had three objects of similar size and density and stuff, it'll be cut in a third. We should talk about this. I know it's not on the slide yet here. Q is the physics symbol for charge. Q is the physics symbol for charge. And I don't know why, but we seem to use capital or lowercase q. Some of the formulas we're going to use, they use lowercase q. Some of these ones here, they use uppercase q. I don't know whether there's really a difference between the two. The other thing you guys should know is that q does not care about positive versus negative. Okay? We don't have a special letter for electrons versus protons. All we care about is how much charge there is, one or the other. Okay? Does that make sense? Okay, here's that induction concept again here. I already kind of showed it to you, but here's another slide of it. Induction is not touching. It's that action at a distance. And if I were to bring the rod closer right here, the negatively charged rods, all of the electrons go to the other side. Just like here, all the electrons went through the metal down into the leaves, and that's why you can see the leaves separate each other. So here's some diagrams. Let's talk about what happened here in these pictures. Let's say that you had a positively charged rod of some type. Somehow you stripped off electrons. And then you had a neutral sphere. Sometimes we call it a pith ball. I don't actually know why, but if you were to come really close, all of these positives would cause the negatives to kind of come this way over here, right? It's not really pushing these positives away so much, it's just causing the negatives to come over here. Well, if you ground this thing, what ends up happening is really electrons are what move, right? So electrons would have to come from the ground up over here and become attracted to these positives, right? So I mean, the negatives would come over this way by induction, but if you had the ability for electrons to come from an external source, the electrons would come through here, and you'd get even more electrons coming up to join this guy, right? Then let's say that you remove the wire. So let's say that you cut the wire all of a sudden. See how the wire is now gone over here? Now what we've done is we've created a scenario here where now, sure, there's still electrons attracted to the positives over here, but now there's extra electrons. You know what I'm saying here? Because more electrons came from the ground to kind of be attracted to that negative. Does that make sense? But as soon as you cut the wire, well, now there's extra electrons here. It would be like if I were to, I don't know, lure my dog into her cage with some treats, and then all of a sudden I just slam the door on her, now she's kind of stuck inside. That's my only way I can get my dog in. I don't know. You guys get the idea what I'm going with here, though? Right? I lure the electrons into the cage, and then all of a sudden, slam the door, now all of a sudden all those extra electrons are stuck here. Right? This would now create an object which is now negatively charged. It was more negative over here when the rod was nearby, which is why they showed a positive over here, because all of the electrons kind of gravitated to one side over the other. But as soon as I move the rod away, well, now the electrons can kind of spread out again, and now the whole pith ball is now negatively charged. That would be a way to create a negatively charged item. And now it will stay that way until you find a way to ground it again. If I were to touch that, well, then now those electrons might move. This, in a sense, is now a Van de Graaff generator. Right? What the Van de Graaff generator does, that big ball in the room back there, is it's a big sphere that has so many extra electrons on it that those electrons can then go to other places if you want. Does that make sense? Here's another illustration I found. You have a negatively charged object, you have a neutral grounded object. Here we're doing the opposite. Here, as I bring the negatively charged object nearby, I'm going to induce a dipole. We're not actually touching these objects, but I'm going to bring the negative right by here, which will cause this side to be positive, and all the electrons are going to go down the wire through into the ground, the grounded wire. They're going away. Well, then if I cut that wire, all of those electrons are now gone. I don't know, as an example here, this would be me needing to send my dog outside to go pee when it's really cold outside. I kind of lure Jaylee outside. Jaylee's my dog, by the way. And I say, Jaylee, let's go outside, I'll give you a treat. And I throw the treat outside, and then I slam the door on her, and then I yell for her through the door, Jaylee, go pee outside. Right? Same sort of idea here. We're forcing all the electrons to go away, and then I cut it, and then now all those electrons are stuck outside, and we're left with a positively charged item. Does that make sense? So we can create negative and positively charged items by inducing a charge on a grounded item, cut the ground. It doesn't have to be a wire, it can just be me touching it or something like that, right? When I put the stick next to it here, and I've now made that negatively charged, all I have to do is this, and I've soaked all the electrons through me, right? I have now become the ground, and then once I'm done with that, then when I take my hand off, well, now it's back to being neutral, right? Kind of opposite thing here. Once I've done this here, now it'll stay. This one was the negative one we started with. This is the positive one we have afterwards. Does that make sense? Yeah. So here's actually the tool I used. So sorry, Tom and Brady, I know you guys can't see this all as well. This is an electroscope. It's basically the picture of what you have right here. It's basically inside an insulated box so that nothing can somehow, you don't want it to get grounded. If you guys can see here, by the way, if I take it apart, okay, I won't take it all the way apart. Can you guys see what this is right here? It's like a rubber stopper. Why is it made out of rubber? It's a good insulator. Does that make sense? Because what I don't want to have happen is all the extra electrons to go into this box, or into this glass, or go through the table, right? Because if that's where all the electrons went, then I wouldn't be able to see it on the two little pieces of metal here. So ideally, this is basically inside essentially it's supposed to be a closed system. You know what I mean? Where nothing should be able to get in and out, except through the ball at the top here. That's the concept. And then, yeah, the leads should separate as you induce a charge getting closer. So. Okay, we must be getting close to being done. It doesn't matter whether it's negative or positive though. Right? Here's a diagram showing both. Here, if I bring a negative object nearby, it forces electrons into the wire, and then two negatively charged leaves will branch out, right? But let's say you brought a positive item. Well, what's going to happen to the positive item? All of the electrons that were naturally inside the electroscope will be sucked up towards the top, leaving two positively charged leaves. Well, then the positively charged leaves would then separate. Here I've got another diagram. Let's walk through what should be happening here. Here's the charging by contact. The better word for this would be conduction. So, neutral electroscope, I touch the negatively charged item on there. The electrons literally go through it. Everything becomes more negatively charged. You move the rod away. Well, not everybody's still negative. These two leaves, they separate due to positive and negative, like charges repel, right? Whereas here's the induction one. I guess it's already written down there, right? Induction, I bring the negative close. All of the positive comes to the top. All of the negative goes down to the bottom. Now, if I have a ground right here, I can actually have all of the negatives just go into the ground, and you see how nothing happened to them. Right? If I were to try to do the exact same thing here, and I want to bring this close here, but I'm touching it, well, now nothing's happening, right? Because I'm just adding or providing an extra outlet for the electrons to go through. So you don't want to have the ground, but if you didn't do that, then you could make it so that it was positively charged afterwards, and then all of the electrons came from this guy right here. There would have been electrons here. The electrons actually went through the ground as they got brought up. Does that make sense? Like all the electrons got forced as far away as they could go. Ideally, you want the electrons to go down here, right? And if the electrons went down here, the leaves would separate. But because you grounded the thing, the electrons, sure, they might have gone here, but even better, they might go way the heck over here, cut the wire, this thing now has fewer electrons, now it's positive, now it separates. Probably showed you enough pictures right now. Do you guys have this slide? Okay. One more change. We didn't do any math today. We didn't do any calculations. It was all theory and understanding. This is a shift for me because I don't usually do this a lot, but you guys are going to want to read your textbooks. Because really, that's what you're doing in lieu of doing any work, right? Like I can't say, here, try questions 1 to 4, where you do a bunch of math calculations. This is more of a, do you get the concepts? Right? And so, I mean, I've showed a video, I've explained it to you, I've done a bit of a demo here, but you guys are just at this point here. It's not necessarily a whole lot of fun to read through scientific textbooks, but you probably should. At least give it one read through just to solidify, and maybe you'll pick up on something that you missed otherwise. So at the end of each of these notes from here on, I'll probably have a slide that says, go read this. Yeah, if you guys don't have textbooks and never used them before, go grab one. So you're kind of going to need them from here on out just because the scope of the course changes. So, okay, quick summary, and I'll stop talking because it's been a long lesson here. We're changing gears quite a bit here. This is much more theory than math. It's more understanding and application of how things work. So the idea basically is action at a distance. What forces exist that are not just like directly applied forces where, sure, I can push something, but what natural forces are there? We've already talked about gravity. Today we're starting a unit focusing on magnets and electrostatics and charges. And we'll talk about how these two things, they actually weave into each other and how they're actually very similar. So, you guys probably know most of this already. Positives attract negatives, positives repel positives. We can use things like this to see the effects of what's happening. We think we understand what's going on down there. But, I mean, Kinsey was watching the Magic School Bus this morning before I went to work here. You guys see the Magic School Bus, right? If we had Miss Frizzle in her Magic School Bus and she shrunk the bus down to like the size of atoms in there, we would not see anything though, right? An electron and another electron, there is not matter that exists between this electron and this electron, and yet the electrons will want to separate each other. Does that make sense? She wouldn't be able to land the Magic School Bus on some sort of magical line that goes in between them. And that's where we'll talk about fields later. The idea that as a way to explain why this occurs, there must be some sort of explanation. So all we can sometimes do is see the effects of what's happening, and we have theories about what's occurring, but this is a lot harder to test. I can't just look and go, what is in between there? Because there isn't something there, right? This is, I don't want to call it magical, because it's not magic, right? But this is getting to that part of like the unexplainable where we're still working through trying to fully internalize how these things work. You guys get where we're going with this? So I think you'll like it. It's fun, but it's definitely a different side of physics. Okay, you guys have any questions? I was very redundant today and kind of said the same thing about 9 times. Okay, so take a break, grab a textbook. We have like 10 minutes left, so there's not much. So thanks for bearing with me.